Law of conservation of energy. In our previous video, we have learned that energy occurs in various different forms, such as potential energy, kinetic energy, light energy, heat energy, and so on. All these forms of energy, they can be changed from one form to another form. Now, what happens to the total energy of a system during or after the process? Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. That is, it can neither be created nor be destroyed. Therefore, we can say that the total energy before and after the transformation remains the same. This law of conservation of energy is valid in all situations and for all kinds of transformations. To understand this, let us consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy of the object is mgh and the kinetic energy will be 0. The total energy of the object thus becomes mgh. As the object started falling, its potential energy will change into kinetic energy. Let us suppose that v is the velocity of the object at a given instant. Then the kinetic energy would be represented by half of mv square. As the fall of object continues, the potential energy would decrease while the kinetic energy would increase. And when the object is about to reach the ground, at that time h will be equal to 0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy the least. However, the sum of the potential and kinetic energy of the object would be same at all points. That is, potential energy plus kinetic energy is equal to constant. Or we can also write it as mgh plus half of mv square is equal to constant. The sum of kinetic energy and potential energy of an object is its total mechanical energy. So, during the free fall of the object, the decrease in the potential energy at any point in its path appears as an equal amount of increase in kinetic energy. Students, you should remember that the effect of air resistance on the motion of the object has been ignored in this case. Therefore, there is a continual transformation of gravitational potential energy into kinetic energy. Rate of doing work. Do all of us work at the same rate? Do machines consume or transfer energy at the same rate? Agents that transfer energy do work at different rates. Power measures the speed of work done, that is, how fast or slow work is done. We can define power as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time t, then power P is represented by power is equal to work upon time, or we can also write it as P is equal to W by T. The SI unit of power is watt, having the symbol capital W. Now, 1 watt is defined as the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 watt when the rate of consumption of energy is 1 joule per second. We can also express the larger rates of energy transfer in kilowatts. 1 kilowatt is equal to 1000 watts. We can also write it as 1 kilowatt is equal to 1000 joules per second, because we know that 1 watt is equal to 1 joule per second. The power of an agent may vary with time. This means that the agent may be doing work at different rates at different intervals of time. The average power is given as the ratio of total energy consumed to the total time taken by the object. Commercial unit of energy. The commercial unit of energy is called kilowatt hour. What is 1 kilowatt hour? It is the energy used in 1 hour at the rate of 1000 joules per second. Now, 1 kilowatt hour can be converted into joules as shown here. 1 kilowatt can be written as 1 kilowatt into 1 hour. We can also write 1000 watts instead of 1 kilowatt, and if we convert 1 hour into seconds, it will be 3600 seconds. Therefore, 1 kilowatt hour is equal to 3.6 into 10 raised to power 6 joules. The energy used in households, industries and commercial establishments are usually expressed in kilowatt hour. For example, electrical energy used during a month is expressed in terms of unit, and 1 unit means 1 kilowatt hour.